Good morning and welcome everybody to today's SunSpec webinar entitled Powering Flexible Grids with 2030.5. This webinar is being promoted and coordinated in partnership with our newest authorized test lab, Codibly. We're excited to work with Codibly and welcome them to the Alliance. Codibly is bringing a valuable contribution to the test lab network with a unique software focus. So we're excited to give them the opportunity to talk with you all today and see what we can learn from them as they've in their experience with deploying 23.5 networks and testing with 23.5 products as well. All SunSpec meetings are conducted in accordance with the SunSpec antitrust policy and intellectual property provisions defined in the SunSpec member agreement. This agreement can be found at the following address. SunSpec strictly prohibits market participants and their employees who take part in these activities from using their participation as a forum for engaging in practices or communications that violate antitrust laws. Confidential or proprietary information should not be discussed in open session. Please contact SunSpec management if you have any questions. Before I pass it off to the Codibly team, a couple housekeeping items. This webinar is being recorded, so we will distribute the slides and the recording after the meeting. We do ask to keep the background noise to a minimum, that you keep yourself on mute and your cameras off if you don't intend to be seen or heard, and definitely want to keep the background noise to a minimum as well, of course. Additionally, we ask that you put your questions or comments into the chat. We will have some time at the end for some Q&A where we'll read through the questions and perhaps have an opportunity if somebody wants to ask a live question at the end to unmute and ask a question. Depending on the questions we get in the chat. If you have any questions, so you're going to be hearing from President of Codibly, Spencer Borison, and Senior Technical Consultant, Patryk Bober. They'll be introducing themselves. You can see Spencer's contact here if you have any questions or want to get into contact with them after the meeting. And of course, SunSpec, we're always available for your reach outs and your questions as well. You can contact us at membership@sunspec.org anytime. So with that, I'm going to keep my comments short and let Spencer and Patryk get right to it.
Okay, great. Thanks, Dylan. And I'll keep moving us along here in the slides. And thanks everybody for joining. Looking forward to having a good conversation today. And like Dylan mentioned, if you have questions, please feel free to drop them in the chat throughout the discussion. And we've reserved some time at the end, as you can see here in the agenda, for going through them. So just a quick overview. We'll spend 1 minute here and then can dive right into it with an introduction and some of the content that we prepared. We want to talk a little bit about two major areas. One is the state of IEEE 2030.5 and the broader demand response flexibility market today from a regulatory and policy perspective. So I'm going to spend 10-15 minutes talking about that. And then my colleague who leads our demand response program work on the more technical side, Patryk, who you'll be hearing from on the second half of this webinar, will do a bit of a deep dive into some of the technical architecture and project implementation that we have done in the past with IEEE 2030.5, both on the client and the server side, which we'll explain more about that for those that aren't familiar. And we'll also share some lessons learned in terms of some of the key things to be taken away from thinking about a technical implementation for what we consider to be a very good and strong standard for demand response and flexibility in this market. And then I'll end with just a brief takeaway, some of the business implications for manufacturers, OEMs, as well as utilities and other players within this general industry. And then, as I mentioned, we'll open up to Q&A. So that's the general agenda. We're already 7 minutes in, so I'll keep it moving so we don't run out of time here for the Q&A session. So very briefly, I'll introduce myself. I lead Codibly's US business and act as the president, and have been around in the industry for about a decade. Much of the work that we do as Codibly, which I'll explain a little bit more in the end here, is within this demand response, DERMS, VPP space. We act as a technical partner. So we're a software services company with about 2,000 people and help customers and clients across this ecosystem, both OEMs as well as aggregators and utilities, to understand different standards, whether it's IEEE 2030.5 or OpenADR or OCPP or any of the other key protocols that enable for certain aspects and use cases of demand response. We help them to understand and then actually implement and certify those implementations. so that they can be compliant and participate in important demand response topics in the market. So excited to be helping lead this webinar. And Patryk, I'll quickly turn it to you for a short intro, and then we can dive right in.
Sure, thanks, Spencer. Hi, everyone. My name is Patryk Bober. I am a renewable energy consultant at Codibly. I come from a software engineering background, and I've spent the last 3.5 years here leading projects in the renewable energy and demand response domain. A large part of that work is integrating OpenADR and IEEE 23.5 on both the utility side and on the aggregator and OEM side. Alongside the customer engagements, I also lead the internal team that builds the so-called accelerators we use across those projects. So great to be here, excited to be here.
Okay, awesome. So without further ado, I will provide a little bit of an overview of what we see in the market. This presentation is going to be primarily focused on the United States, but that being said, we do have a slide, and the SunSpec Alliance was keen to make sure that we point out that there are a lot happening outside of the US as well. So this standard definitely applies well outside of the US, and you'll see that on one of the slides as well. But just for the purposes of the scope of this presentation, we'll focus primarily in the US here. So very high level, just very quickly, I know many of the participants here probably already know what a standard communication protocol is, but just wanted to quickly define it. So really, we think of it as a common language. It's a set of definitions and procedures that allow some sort of controller, whether that's a utility or an aggregator, to communicate and control end devices. So communicate with them in some protocols and be able to actually have some control functions in others. Some of the key protocols that we see in the market, of course, you'll see the second one is IEEE and the CSIP, which acts as the Common Smart Inverter Profile, which is a subset and a tailored set of use cases and test cases within the broader 2030.5 spec that allows really for inverters directly to be communicated with and controlled. So there's also OpenADR, which is more of a communication standard and typically manages resources between aggregator and an end device in a top node, end node topology. 2030.5, as I mentioned, it's a system level interface used by utilities to tell systems what to do, either through an aggregator or a local client that translates to another device protocol. And often we'll see that paired with the fourth one here, which is also something that SunSpec helps to manage, which is the Modbus, SunSpec Modbus protocol. So you'll see we don't really go into super detail here on SunSpec Modbus on this presentation, but they are very much aligned. And so it's important to know about both of them if you're thinking about this broader implementation journey. And then there's a couple others, IEC 61850 and DNP3, which are important for specific use cases, but we're not going to go super deep into those today. Okay, so wanted to start, I'll start high level, and then we'll go into some specific states and markets where there are interesting things happening. So on the federal level, I think some of this might not be news to folks, but there's a couple key things that are important to note when it comes to demand response and flexibility, two of which come on the federal level from FERC, which is the governing body at the federal level for energy markets. So the first was in 2018, number 841. That allowed for electric storage resources to participate in markets operated by RTOs or ISOs, which are the major market operators within the United States. Important to note, this as well as the next one excludes ERCOT because of the way that the Texas interconnection sits separately from FERC's jurisdiction. That being said, as you'll see in one of the state slides, there's plenty going on in Texas. So not to say they're not doing anything, but that they're not directly covered in this FERC order. So just a fun fact and something to note. The second is sort of an extension then of 841, which is often called quadruple 2 or 2222, which came out a couple years ago. And this allows for the broader participation of distributed energy resources to participate as aggregations in these markets. So this really opened up the valve for DERs and aggregated resources to participate in demand response, which is really exciting and has opened a lot of different market opportunities that we'll talk about. And then the key overarching standard, IEEE 1547. Typically, we look at the 2018 version. This is the set of technical specifications that defines performance for DERs connected to the distribution grid. And importantly, within clause 10, basically it says that a DER to be able to connect within this protocol needs to have one of three protocols implemented, IEEE 2030.5 being one of the ones that's most often used, as well as DMP3 and SunSpec Modbus. So typically when we're looking at state level and also utility level regulations and programs, there's some level of adoption of IEEE 1547, and we can then imply directly from that that one of these standards, including IEEE 2030.5, is relevant and important for participants in that market, or aspiring participants in that market, rather, even to be thinking about and to potentially implement as well. So that's a high level context. Next, I'll go into specific areas where we're seeing adoption. So let's start on the international level. I'm not going to spend a lot of time here, but this is more just to show you that this is not just a US-based 2030.5 adoption story, but rather that 2030.5 occurs and is used in various ways across many different major markets in the world, as well as is very well in the conversation now in Europe. So something to consider, that as you're a global company or you have global ambitions, this is not just for the US, this is also applicable more broadly. Then wanted to talk a little bit about the US states to keep an eye on. This is something actually that comes from DESRI, which we've got a link to this resource. I think it's actually super useful. And some of these, you may even be able to track some updates to some of the state adoption status. I just wanted to call out a couple things. So here in the coloring, you can see there's a complete or an ongoing, which is this green or light green. And then there's also a purple, which is utility specific. And that's probably the two areas that are most useful in terms of this map. The red, not so important at the moment. But the purple means that specific utilities are working on requiring 1547 and therefore IEEE 2030.5 as a part of participating in the programs in various ways that they're running. It may not apply across the full state, but it might be specific to a utility. And so it's important still to look into the details within those utility programs and requirements, because it may still block or, once enabled, allow you to participate in a key part of that market. And then you can see some of the key states here. I'm going to dive a little bit deeper into a few of them that we think are some of the interesting emerging states. I'll mention, and I've got another slide towards the back, that California has and continues to be at the forefront of some of this regulatory work, as well as some of the adoption and testing. There's a number of different standards. Folks have probably heard of California Rule 21, which is a requirement for IEEE 2030.5 for inverters through this CSIP subset, like I mentioned. And then there's also a number of other things for building codes, Title 24, and they also have now a evolving standard through the Flexible Demand Appliance Standard, FDAS, which is starting to roll out and has its first device category. And then they're going to continue to cover more and more device types over the next few years that explicitly prohibits you to continue selling that device in the state if you don't have some sort of flexibility requirement met. So the first device class that's covered there is actually pool controls. So Codibly's helped a couple customers to work on meeting the requirements for that standard, but it's going to expand into other types of device classes as well. So important note on California, but I'll put that aside because that's not where I think people may overlook other states in terms of what's happening. So I wanted to quickly talk about some of those. The first is Texas. So like I mentioned, when I was talking about ERCOT being outside of FERC's jurisdiction, there is a lot going on in Texas and specifically within ERCOT. So you can see here, there's a couple different legislation pieces that I think are important. So the first would be the Senate Bill 1699. And basically what that did is it allowed and sort of mandated that we want to have more residential load reduction through demand response programs. They set a 20% threshold target. And they've also paired that with a program that's in progress called the ADER, which is Aggregate Distributed Energy Resource Pilot Project. which is aiming to increase the capacity of some of these key characteristics for contingency reserve, demand response, and other types of capacity. So paired together at the ERCOT and at the state level, there's a lot of incentive now and some programs that are in place that are helping to motivate the adoption of some of this flexibility and the protocols that enable it. And then, like I mentioned, down to the utility level. So some of the utilities are already well along the way and have already mandated the adoption of 1547. So AEP Texas, which you can see primarily sits in that sort of spread around certain different areas of the state, actually. They adopted in 2024 this requirement, and Austin Energy is also in the late stages of adopting that as well. So there are certain key utilities where we have a requirement for participating in the programs that they're managing, even if it may not be a requirement across all utilities at this point in Texas. But there is a lot of momentum and a lot of investment happening based on how the Texas market is structured. And so it's definitely a hot topic and something to keep an eye on. Okay, going to the next state. I have, I believe, 3 that I'm covering here. So the second is Illinois. So there's a set of House bill and Senate bills. You can see the number there that are in progress. They were brought actually in 2024. That did not move forward, but in 2025 they were brought again, and I believe it's still being worked through some of the committees, working towards a final vote soon. Someone hold me to that if I'm misspeaking in terms of the current progress, but the last time we checked, that's where it sits. These create and provide the incentive to create a virtual power plant program across some of the key utilities in the state. And that's meant to be sort of a standalone energy storage distribution deployment program and other types of demand response that enables VPP. Then there's a couple utilities of note. So ComEd and Ameren, which both have this BE plan already in place or in progress, which is the beneficial electrification plans. They are basically working to invest in upgrading the grid and creating sort of an integrated grid plan, which would enable and propose VPP capabilities and flexibility within the markets. So there's a lot of pilots happening already at ComEd and Ameren around these topics, and the protocols are starting to become a major player in some of those programs and pilots. So something to also consider. And then finally, Colorado. So there was a bill passed, Senate Bill 218 in May of 2024 that required Xcel Energy to propose a VPP program in the coming years. There are a number of dockets that I've shared here around their steps to do that. And since this slide was made, they've actually gone through and selected already a DERMS vendor that I believe is publicly available, but I'll let you look that up. And they've already started to go through what they're calling the AVPP program to set up some initial programs in Colorado and then to expand that into some broader territories across the region. So there has been some significant progress from Xcel, and I know that they're using some of these protocols directly. There's also the Public Service Company of Colorado that has been issuing some RFPs trying to help with addressing some of their distribution system needs. And one of the topics within that broader RFP is DER integration, also looking at some of these protocols and how they play a role in that integration. And then finally, like I mentioned, there's a couple other states. I'm not going to go into too much detail here around them. I mentioned California already. There's also the WattSmart program. I think that's the other one I'll call out here. We've done a couple implementations in Utah. The latest that we checked as well, Washington State also has this program available, the WattSmart program. It's sort of under the PacifiCorp company family, of which Rocky Mountain Power and Pacific Power are a part. And that's specific to batteries and mandates IEEE 2030.5 as part of program compliance. So if you're looking at California, if you're looking at Utah, if you're looking at Washington State, IEEE 2030.5 is explicitly mentioned as a requirement for certain device types. And it's also something that has a lot of applicability across a lot of other states and utilities within many states. So that's the takeaway from my side. Again, if you have questions on this part of the presentation, please do feel free to share in the Q&A. And otherwise, I'm going to pass to Patryk to spend about 15 to 20 minutes here walking through some of our technical findings and learnings and some things that might be applicable to the audience that we have on the call today. So I'll pause, and Patryk, over to you.
Thank you, Spencer. So if you could please go to the next slide and we'll start. Okay, so let me set the picture before we go deep. At Codibly, we ship 23.5 server and client-side integrations on both sides of the wire. On the left of the diagram, the utility backoffice holds the operational logic, advanced distribution management system, DERMS, market systems, billing, and the IEEE 23.5 server is one of several outbound surfaces from the backoffice, sitting alongside other protocols the utility uses for substations, other utilities, and the wholesale market. From the 23.5 server, you can see two arrows, both labeled IEEE 23.5, representing two topologies that sit side by side in real deployments. The top arrow goes directly to a DER, the case where the DER runs the 23.5 client itself. Native support is rare in practice, typically limited to grid-scale assets and a few modern smart inverters with CCP-certified stacks. More often, this direct path is a local client or edge device that speaks 23.5 to the utility and translates to another protocol downstream. The second arrow goes through a 23.5 aggregator client, which is how behind-the-meter and consumer-scale assets typically reach the utility. The aggregator client speaks 23.5 northbound to the utility, and southbound speaks whatever the assets actually understand, which is where the not specified labels come in. Past the aggregator, the protocol depends on what the asset is. OCPP for EV chargers, Modbus for inverters and battery systems, and vendor-specific cloud APIs in fleets where the OEM owns the device management layer. There is no single standard for what lives on the right-hand side of this picture, and the absence of one is part of why the aggregator role exists. The aggregator absorbs the protocol diversity behind a single predictable 23.5 surface that the utilities ADMS or DERMS can talk to without needing to know what's actually plugged in at the far end. The takeaway, 23.5 standardizes one specific boundary, that handoff between the utility and the aggregator client, and everything around it on both sides is the integrator's responsibility, which is exactly where the rest of the stock is going. So let's go to the next slide. Okay. With the framing in place, let me show you what the server side actually looks like in production. The diagram on this slide is the high-level architecture from one of our recent server-side projects, deployed as a single cloud system that connects utilities DERMS to the IEEE 23.5 ecosystem. Reading the diagram from left to right, the DERMS sits on its own as the existing operational platform owned by the utility, and it talks over HTTPS to the 23.5 server through a dedicated DERMS API, which is the integration seam where the customer-specific work happens. Inside the IEEE 23.5 server box, you can see two halves, the DERMS API on the inward-facing side and the IEEE 23.5 server API on the outward-facing side that the clients connect to over 23.5. To the right of the server, two clients are shown, a direct DER client and an aggregator client, both connecting over 23.5. The server treats them the same way at the protocol level, even though the integration patterns downstream of each look quite different, which is something we'll come back to on the client side. Below the server, there are two databases, a relational SQL store for the end device records, group and program definitions, certificates, and the rest of the operational state, and a time series database that receives telemetry as it derives from the clients. Everything in this picture lives inside a single cloud environment, which keeps the operational footprint consistent across deployments. This is where what we call our accelerator comes in, a generic protocol layer with out-of-the-box features on top of which we build the customer-specific integration. For the server side, the accelerator covers the communication with clients over 23.5, and device creation and registration, group and program management, the the publish-subscribe mechanism, PKI and certificate handling, and telemetry ingestion into the time series store. That is the part we don't write again from project to project, because the spec is the same regardless of who the customer is. The work that's specific to each engagement sits on the left edge of the diagram, where the server connects to whatever DERMS or utility back office platform is already in place. And that connection can take the form of an HTTP API, a message bus, or another integration mechanism, depending on what the customer's existing stack runs. Let's move on. Cool. So there are a few common reasons a utility or DERMS vendor decides to bring an 2035 server into its stack, and the slide on screen lists the ones we encounter in our engagements. So the first is regulatory. As Spencer mentioned, in some markets, the utility is obliged to expose a SysIP-compatible interface as part of the interconnection process for distributed generation, with examples being California's Rule 21 framework. Second driver is onboarding third-party aggregators and virtual power plant operators into utility programs. Without a 2030.5 server, the utility would have to build a separate connection for each aggregator, which doesn't scale. Demand response and peak curtailment programs are another common driver, since the server provides a structured way to issue time-bounded events to broad groups of devices without hand-rolling a control path for each fleet. Dynamic export limit programs appear as a driver in markets where behind-the-meter solar capacity is high enough that feeder constraints matter, and the utility needs to publish a time-varying envelope rather than rely on a fixed limit. Telemetry visibility into DER the utility does not own is a use case in its own right, because once the server is in place, the utility starts receiving real-time and aggregated readings from fleets it previously had no protocol-level visibility into. Now let's go to the next slide. So now let me show you the equivalent picture on the client side. The diagram on this slide is the high-level architecture for an aggregator client we've delivered, and it's drawn intentionally to show several integration patterns side by side, even though no single deployment would normally use all of them at once. The 2030.5 server in the top left is the utility side endpoint we've already talked about. Inside the cloud environment, the 2030.5 client has two halves. The 2030.5 client API on the left, which speaks 2030.5 northbound to the utility and is built on our accelerator, and the DER communication module on the right, which handles all the southbound integration to the actual assets, and this is the part we implement on a per customer basis. On the right of the diagram, you can see three different ways of the DER communication module can reach out, and again, a real deployment would normally use one or two of these rather than all three. The first option is a vendor cloud API over HTTPS, which is how you'd connect to a fleet of consumer batteries managed by their OEM cloud, for example. The second option is Codibly's own OCPP server, which the client uses over HTTPS and which then speaks OCPP downstream to EV chargers, which is a natural fit for managed charging programs. The third option is a connection to an edge gateway over, for example, MQTT, where the gateway then talks SunSpec Modbus locally to inverters, batteries, and PV systems on the same site. This is one of the most common patterns in real-world deployments, and also the most semantically aligned with 2030.5. SunSpec Modbus and 2030.5 share the same DER concepts and behaviors, so the translation work is structurally simpler than with the Cloud API or OCPP options. The combinations are flexible. The 2030.5 client itself stays the same regardless of what sits on the right edge of the picture. So the per project work concentrates inside the DER communication module. One more thing worth mentioning here, even though it's not on the diagram, for any of these integration paths, we can plug in our DARE simulator, which can stand in for multiple DARE assets, react to events arriving from the utility, and generate and send realistic telemetry back, which lets the integration be exercised end-to-end before any real device is connected. Next slide, please. So before we move into use cases, let me take a moment on what's actually inside the client accelerator out of the box, because this is the part that customers don't have to build themselves. On the protocol and security side, you get a hardened MTLS implementation against the utility's 2030.5 server with configurable certificates and cipher suites. So each utility's mandates can be matched without code changes, and you get all of the SysIP required function sets ready to use. On the resource and lifecycle side, the accelerator handles end device registration and management, program and group membership through their programs and functions of assignments, and the subscription and notification machinery that keeps the push channel alive with the server. On the control logic side, the accelerator implements primacy and supersession across overlapping their control events, and the randomized start logic that prevents a fleet from snapping in lockstep at event start. All of this is the part we wrote once. The per customer work, as we just saw in the previous slide, sits inside the DARE communication module. And let's go to the next slide. So with the accelerator features covered, let's turn to the client-side use cases. The drivers here mirror the server-side ones, since each driver shows up from both sides of the wire. Where the server side requires the utility to expose a 2030.5 surface for interconnection compliance, the client side requires the aggregator or OEM to demonstrate that DER under their control can respond to utility commands at the protocol level. Where the server publishes a time-varying export envelope, the client has to enforce it on solar and battery export, hour by hour or minute by minute. Where the server-side managed charging program issues events to back off charging during grid congestion, the client is the protocol level path that carries those instructions to the chargers. And where the server hosts a VPP program contracting capacity, frequency, or voltage support, the client is how the fleet actually delivers and reports that. The last driver on the slide is more specific to the client side. In markets where a single fleet operates across multiple utilities, which is the case for many large EV charging networks and aggregators, the 2030.5 client provides a single consistent surface for talking to all of those utility servers from the same fleet platform. And let's go to the next slide. Thank you. With the architectures and use cases covered on both sides, let me spend some time on what the integration work actually looks like in practice, because the SysIP profile by itself is rarely the full picture. The diagram on this slide shows how the layers stack up. At the bottom is the IEEE 2030.5 specification itself. The next layer up is SysIP, which is the most common profile of 2030.5 used in utility programs today. Above SysIP sits SysIP OS, which is an Australian extension that adds explicit import, export, and load limit fields. And SysIP OS is also used outside Australia in some cases, because those explicit limit fields fit naturally into managed charging programs elsewhere in the world. The top layer is the per utility profile, where each utility adds its own rules on top of SysIP. Those rules can be driven by the utility's back office, by the specific program being run, or by the type of asset being integrated, since storage adds storage-specific controls, EV chargers bring their own constraints, and rooftop PV brings yet another set. None of those per utility deltas are in SysIP itself, but all of them are real code on the client side. Where the accelerator helps here is straightforward. It takes care of the SysIP foundation layer end-to-end, so the customer's effort during integration concentrates on the per utility specifics rather than on the protocol layer. Now, let me make this concrete. The categories on the slide come from two real utility requirement sets, a North American utility and an Australian distribution network service provider, and they generalize across most of the utilities we encounter. End device modeling and registration vary between deployments. SysIP supports both single-site and aggregated end devices, with aggregated ones sometimes acting as VPP-style aggregations, where child DAREs are reporting only at the protocol level. Registration can be in-band or out-of-band, with utilities differing in how they tie aggregator registration to a metering identifier or connection point. LFDI derivation rules also vary from market to market. Telemetry is where utilities are most specific. The North American utility requires per DARE metrics, real and active power, voltage, frequency every 5 minutes alongside their status, plus real-time alarm updates. And in VPP setups, aggregated telemetry on top, including net active power for the whole fleet. Metrics also differ by asset type. EVSE telemetry covers three-phase voltage and total real and reactive power, while EV telemetry focuses on state of charge. The DNSP requires UTC-aligned post rates and is specific about how the underlying real and reactive power values should be calculated, preferring hardware integration of energy over the post period with sampling as a fallback. Capabilities and settings include required fields like storage ratings and supported modes, with extra fields for storage assets, the DNSP's charge and discharge rate ratings, and a minimum energy floor, for example. Availability and event logging are present in SysIP, but typically optional and contract-driven. DER controls and operations vary the most. SysIP Australia contributes import, export, and load limit fields used in managed charging. The DNSP adds storage target operation mode for storage set points. The North American utility raises the minimum stored event count from 24 to 72. And it also expects DER controls to reach the device within 5 minutes. The DNSP requires storage control response within 15 seconds aligned to Australia 4777.2. That's the shape of where the customer-specific work lives. The accelerator covers the SysIP foundation, so a real integration project is mostly about working through these categories against each utility's handbook. And let's go to the next slide. So all of these requirements have a practical consequence: testing. SysIP certification by itself covers protocol level conformance through the SunSpec test procedures, but it doesn't cover any of the utility specific deltas we just looked at. The accelerator is pre-tested for SysIP compliance, which gives every project a strong starting point, and each customer still goes through their own SysIP certification round after their integration is built. That's a step we walk with them on every engagement. We are now a SunSpec authorized SysIP test laboratory ourselves, so the certification testing can sit inside the same engagement rather than going through a third-party lab. The per project test work then concentrates in the next two stages on the slide. The first is the DARE simulator pre-flight, where the integration team rehearses the utility's specific scenarios with simulated DAREs reacting to events and producing telemetry well before any physical device is connected. The simulator can stand in for whatever asset mix the project involves, so the storage or charging specific behaviors that the utilities tests usually exercise get tried end-to-end in a controlled environment. After that, the integration moves into the utility's own test environment, where it is evaluated against the utility's specific test suite. On the North American side, that means going through the utility's integration test environment with their specific test cases before being allowed into production. For the DNSP, it means a custom test suite that extends beyond the SysIP baseline particularly around the storage extensions and asset-specific behaviors that are not covered by default. Both the utilities test environment is where the per utility deltas are evaluated end-to-end. And let's move to the next slide. So all of this, the variation across utilities, the testing path, the per customer integration work, it's what Codibly helps with. And the slide lists the things we deliver across our engagements. The two accelerators are at the core. The 2030.5 server accelerator for utility and DERMS deployments, and the client accelerator for aggregators and OEMs. Both are pre-tested for SysIP compliance and bring the generic protocol layer ready to use. Alongside the accelerators, we ship the DER simulator, which stands in for real assets during the test phase, generating telemetry and reacting to events end-to-end. On the services side, we deliver the per customer integration work itself, the DERMS API on the server side, and their communication module on the client side, wired in to whatever the customer's existing stack needs. The shape of the downstream integration varies project to project, and one example is our OCPP server, which we use when the customer needs managed charging through an OCPP backend. And we walk every project through SysIP certification and the utility's own test environment. The protocol layer is already done, the testing tools are already there, and the integration team focuses on the parts that vary between utilities. And let's move to the next slide. So 3 things from this section to hold on to. 1, 2030.5 standardizes one specific boundary, the utility aggregator handoff, and everything around it is integration work that varies by customer and utility. 2, SysIP gives you the protocol foundation, but utility-specific deltas across end device modeling, telemetry, capabilities, and controls are where most of the integration effort actually concentrates. 3, SysIP certification is one step in the testing path. Each utility runs its own test environment on top, and exercising the integration end-to-end ahead of going live is what catches the misalignments. So that's it from my side. And back to Spencer.
Okay, great. Yeah, thanks, Patrick. And for those still with us, I see a couple of questions are starting to trickle into the Q&A. So glad to see that, and we'll answer those questions in just a few minutes. I've just got like 2 minutes of slides here, and then we're gonna dive into your questions. So feel free to continue to ask those in the chat, and we will try to answer as many of those as we have time for. So just a quick overview, I guess, to bring it all together. So Codibly, like Patrick mentioned, has these pre-built accelerators. We also act as a partner to a lot of the organizations you see here below. So not only SunSpec, where we're proud to be the newest member, but also the OpenADR Alliance, where we're their technical implementation partner. And we also partner with a number of aggregators to help enable demand response across different device classes and residential, commercial, industrial scale type assets as well. So we do a lot of work in this space. We have a lot of expertise, but we also do a variety of different custom software development work with a team of almost 2,000 people globally. So anything in the software space related to the energy industry, we've got deep domain expertise and a strong technical capability to be able to design and deliver products and integrations and services that help our clients across the world. And I think with that, I'm going to skip ahead a little bit. I think we've talked pretty much at length about these accelerators, but maybe just one question I saw that came in around what the accelerator is in a little bit more detail. So I'll quickly answer that question, Melanie. So the accelerator typically is a pre-built, like Patrick was mentioning, a fully pre-built solution. So we think of it as a code base, can also be called a Docker container. It's a microservice basically that helps accelerate the implementation of this IEEE 2030.5 or any of these other standards and integrations that you see on this slide. And we do it in a accelerated timeline where our team will do the heavy lifting, both to help understand your existing infrastructure, and then we'll actually license you the access to that code base. We then provide that license on a perpetual basis, so you have that for forever, and you can make any modifications. It's a fully permissive license, so you can build on top of the code, modify it, extend it for multiple different projects and utility integrations. It's fully flexible, and our team will lead a small project to implement it within your cloud in a repository and environment that you give us access to, and then we'll do the proper setup and testing, and then finally work with the SunSpec Alliance as an official certification lab that we now are, as has been mentioned, to make sure that this deployment is fully certified. So that's the typical process. And with IEEE 2030.5, the full end-to-end project is typically somewhere like 6 to 8 weeks, and that would include that full process, including certification. So it's fairly competitive in terms of timeline and cost, and something that we have a lot of experience doing. So would be definitely happy to follow up if any folks on this call have questions on that, or want to talk in more detail about how an accelerator for either the client or server for IEEE 2030.5 or any of these others that you see on this slide might work for your business and the goals that you have. So that's what we have, I believe, for the slides. So without further ado, I'm going to turn it to Q&A. And thanks for joining us first and foremost. And then Sam, I guess I'll ask you if there's anything specifically that you're seeing here that you think we should start to take a look at in terms of Q&A for the last 10 minutes or so that we have.
Yeah, no problem at all. I can walk you through some of the questions here, or go ahead, Dylan, if you had something.
Yeah, real quick, just a couple comments before we get to the Q&A. Thanks so much for all of that, Spencer and Patryk. This was really informative and helpful, I think, for the Alliance and for our members and everybody here today. I wanted to highlight two aspects from your presentation. First was the reference you made, Patryk, to the integration and the semantic compatibility between the 23.5 protocol and SunSpec Modbus, because obviously the 23.5 protocol is the dominant method for utilities to communicate with and control DER systems, and we've seen under IEEE 1547 that more than 80% of inverter manufacturers use SunSpec Modbus to comply with that requirement. And together, these things two together really form the end-to-end pathway for standardized communications for DER controls. And so that's something I wanted to highlight, the harmony between those two protocols and the seamless integration. The other thing I wanted to highlight was your focus on the additional utility requirements. Oftentimes, SunSpec's engagement concludes once a manufacturer completes their CSIP certification and they get onto the public key infrastructure. But obviously, there are these important additional hurdles that manufacturers have to go through to finally go deploy these networks and start connecting to the utility grids. And that's an area that sometimes we at SunSpec have less insight into. So I think that perspective and that expertise that you guys bring to the table is going to be really, really valuable for the ecosystem. So thank you for bringing that and highlighting that. So that's all my comments. And with that, I'll pass it off to Sam. If you want to take us through some questions, I'll leave it to Spencer and Patryk to answer them, and I'll offer whatever color commentary.
Great. So we'll just move in the order that they were put in the chat here, starting with Melanie. What does accelerator mean in this case?
Yeah, and Sam, I think I answered that one, so I think we can probably skip to James' question. Yeah.
Is the specific implementation of V2G AC using UL 1741 supplement SC AC profile for the inverter? Oh, this is quite a long question here. SAE J3072, 202406 for the vehicle, and 2030.5 for communications, as I understand it, covered in your slides or in your work not covered here. You might want to read the question just because there's quite a few acronyms.
Yeah. Yeah, no, I get the gist. So yeah, James, thanks for the question. So where we typically operate, we do a lot. So half of our business sits more within like this renewable energy side where demand response and flexibility is a key part, but we also do a lot within the e-mobility space. So we've got a large team that's doing work for managed charging, dynamic load management, V2G connectivity. Certainly, V2G is still an evolving area, so we have some initial pilots that we've done with a number of customers, both in the US and even more so in Europe. And where we typically will add value is understanding some of the integration pathways. And like was mentioned in that previous slide that I had shared, in terms of some of our protocols that we cover with our accelerators, we do a lot of work not only with IEEE 2030.5, which plays a key role here, but also with OCPP, both the 1.6J and 2.01 version, but also the emerging 2.1 version. And we have pre-built solutions for all of those, and also for OCPI for roaming, as it may be relevant to some of that as well. So we have a pretty good grasp in terms of some of the key protocols that might be important when it comes to V2G, and we've done some work also with ISO 15118. So have a pretty good understanding and capability to support V2G exploration and the development of certain solutions that might be complementary to that type of work. Patryk, I don't know if there's anything you want to add there. Otherwise, we can move to the next question.
Yeah. Actually, I wanted to add to answer that. V2G AC is a separate profile that also uses 2030.5, but in this presentation, we only focus on CC basically. So this has not been covered in the slides. Just answering your question.
Great.
So moving on to the next question here from Joe D'Ambrosia. Have you worked with integrating ANSI CTA 2045 compatible loads? CTA 2045 is required for residential water heaters sold in Washington, Oregon, and Colorado.
Yeah, I'm happy to take that one. So good question. And yeah, Joe, so like I mentioned, we're a direct technical implementation partner of the OpenADR Alliance. So their standard with CTA 2045 and OpenADR, they brand as EcoPort. We do have a lot of experience working with that, and have actually done a number of projects for residential water heaters sold in the markets that you mentioned, helping them achieve that certification. So not only using our accelerator that we have for OpenADR, which can do a lot of the heavy lifting, but also we've done some specific implementations of CTA 2045 as well. So I guess a couple things that I can offer that might be helpful here. One, if you go to the OpenADR website, we actually did a webinar on this topic a few months ago that I participated in alongside some colleagues at the OpenADR Alliance and other organizations that are interested in this topic, both talking about CTA 2045 and also the AHR 1380 standard for HVAC units that might be relevant as well, depending on what the breadth of your devices are. So I would encourage you to check that out, and then separately, happy to have a follow-up conversation about what might be relevant for you if you want to follow up with me over email, and the email will be in that slide deck that we'll share on the SunSpec Alliance website later on. I think that's all I have on that topic.
Great, thank you. So moving to the next question, and apologies if I mispronounce your name, Xavier Francia. Have utilities defined unique cybersecurity requirements beyond CSIP? Do you know if any went with unique PKI certification requirements, such as using non-native certificates over native 2030.5 certs?
Patryk, any thoughts on this? And then I may also ask the SunSpec Alliance if you guys have anything to add to this as well.
So as I mentioned in the presentation, the accelerator is open, or has a feature functionality for a specific project or for a specific integration to, for example, configure specific cipher suites. This is something that might differ depending on the utility requirements. The 2030.5 has one cipher specified that all the CSIP certifications needs to follow, but it may change. So this is one thing that comes to my mind.
Yeah, I can offer a couple comments on this one as well. I haven't heard of utilities standing up their own unique PKIs or routes. There was early on in the CSIP development in the Smart Inverter Working Group, this idea was floated, but in those discussions amongst the industry, it was determined pretty quickly that the requirement to support multiple PKIs for multiple utilities would be pretty burdensome, extremely and costly for manufacturers to support. And in addition, once the utilities dug into it and evaluated what it would take to set it up, they determined that most likely they didn't want to take on the associated risk of providing that either. So a combination of risk and cost has led, at least in the U.S., to go in the direction of the one PKI. Now, internationally, what we're seeing as a trend is most countries do want their own route in their own country, within their own territories. So we have seen Australian utilities to set up their own, self-signed PKI infrastructure. So this is one of the opportunities and challenges on the international market. Obviously, it's the same consideration with the cost of manufacturers having to support multiple PKIs. And so one thing we're looking at and exploring is the possibility of federating the PKI routes so that we can maintain interoperability and the countries can maintain their own national security interests as well. So that's something that we do have an eye on, and the industry as a whole will need to grapple with for sure.
Great, thanks, Dylan. So we've got a few more questions here, but we're also coming on time. So if the Codibly team and SunSpec, you don't mind staying a few minutes over, we can go through these questions.
Yep.
Thank you. So the next question is from David Rodriguez. Other than solar inverters, are there any DER device OEMs in the U.S. supporting IEEE 2030.5 instead of their proprietary APIs at scale?
Yeah, I'm happy to start with this one, and then I guess SunSpec would also be curious your thoughts again on this one. I would say from what we're seeing, I mean, 2030.5 is still the most established with inverter use cases, certainly, especially around California Rule 21 and some other programs that we mentioned. There are certainly heavy reliance on proprietary cloud APIs for some of the other device types, but I will say that we've seen some emerging use cases. I guess one that I would call out is in EV managed charging. With one of the California IOUs, we've seen a requirement in a pilot now to have IEEE 2030.5 directly implemented as a way of actually controlling the charger and then being able to have communication with the vehicle for charging. So again, not as robust, certainly, but something that people are starting to think about, and there are some tangible pilot programs. But I'll defer to SunSpec if there's anything else you want to mention.
I have a little bit of a different nuance and take on this. For what we've seen with California Rule 21 and the approved inverter equipment list, is that most of the inverters went the quote-unquote attestation route. So I guess to give you a little bit of context here, when CSIP was initially developed, it was called the Common Smart Inverter Profile. It was designed with the intention of it being applied at the inverter level. However, as deployments or as implementations got going, it was determined that the definition of a native interface was in question, and most inverter manufacturers weren't directly natively implementing it locally within or physically embedded within the device. So California opened up this quote-unquote attestation route under their rule announcement E5000, where manufacturers, there are two pathways to comply with Rule 21. Was yes, you could either have a native 23.5 CSIP interface, or you could do interoperability testing with a CSIP certified gateway with a nationally recognized test lab. And I do believe more than 80% of the inverter manufacturers went this attestation route that proves interoperability. And then, kind of tagging on to something that Spencer said, Rule 21 kind of governs the connection between the utility grid operator and the system level 23.5 interface. So typically it's going to be what we're seeing is the main design is through an aggregator. What happens between the aggregator between the aggregator and the local system might have a 23.5 client to SunSpec Modbus gateway, or actually, because that's outside of the scope of Rule 21, that could also potentially be something proprietary. So that's the reality. The dominant way that we're seeing is going through the utility 23.5 server to the 23.5 aggregator to a 23.5 to SunSpec Modbus gateway at the local device level. So that's where I would, that's my perception of how this has been applied and rolled out.
Okay, great. 2 more questions here if we want to still get through them, guys. You okay with that?
Yeah, let's do it.
Okay, great. Do you work only in the aggregator scenario or also in direct GF-EMS scenario of CSIP?
Yeah, I saw this question and I'm gonna go back. I think Patryk, you may have referenced this in a different slide, so I just wanted to quickly check. Oh, all right, I'm going too far. All right, this I think might address it. Patryk, do you want to quickly talk about that?
Yeah, I I don't want to say too much maybe in here, but if you're happy, then probably Spencer will be happy to discuss it at some later time. But we are actively working on a solution that we could deploy on some kind of edge device on the site, which in this case would be like a direct connect to the utility server without the aggregator, and the solution can speak SunSpec Modbus to the inverters. So we have this option, and we work with this as well, not only focusing on the aggregator, although most of our projects for now were aggregator projects.
Great. All right, moving on to the last question here. Is there a commercial path for making device integrations more cost-effective with IEEE 2030.5? Even if OEMs did support IEEE 2030.5, wouldn't they charge the same setup and per device fees?
All right, Dylan, do you want to answer any of this to start? I'm happy to tag on, but maybe you've got a view on that.
Yeah, I suppose what my initial thought is that you know, there's a very vibrant market for 23.5 CSIP clients. I was just running the numbers yesterday. I think we did like 57. We've done 57 client CSIP certifications, like 30 something aggregators, and like 8 or 9 servers. So there's a healthy market and plenty of competition and multiple vendors if you're looking for a partner to integrate with, to work with, or integrate a 23.5 client to the devices. And that obviously, you know, that's the goal of SunSpec, is to support a vibrant, healthy industry and market with multiple vendors and optionality. So that's kind of been our tactic to address of having costs be manageable, is have a vibrant market where you have multiple options to work with and partner with.
Yeah, I think I don't have a ton to add. I mean, I think that's pretty well said, and certainly, I mean, using an open source protocol doesn't necessarily negate any of the commercial conversation that needs to happen between the OEM in terms of like eliminating all the commercial fees. But I do think it makes it a lot easier from a perspective of, you know, reducing engineering time and test cycles and one-off utility integrations, and just some of the work that would be necessary for integrating between a number of different devices. It standardizes a lot of that, and so we've seen it to be pretty effective.
Right, exactly. Having the standard protocol means that is itself a cost savings mechanism, because you're not having to do custom integrations. So
great. Well, thank you so much for answering those questions there, and thank you to everybody who stayed over time. Again, thank you to Spencer, Patryk, and Dylan for all of your contributions today. Just a reminder, the webinar will be posted to both Codibly website, the SunSpec website, and YouTube, so stay tuned for that. You'll receive an email notifying you as soon as that's posted. And thanks again for joining, and I hope everyone has a wonderful day.
Yep, thanks all.
thank you, everybody. Thanks, Spencer. Thanks, Patryk.
Thank you.
Thank you.
Incredible webinar, guys. Thanks.
Okay,
Thank you.
bye-bye.
Have a great day.